In this video, we'll be focusing on solving IB Physics past problem for topic 3, thermal physics. So this is for HL student, paper 1 question. The first question says, Q and R are two rigid containers of volume 3V and V respectively, containing molecules of the same ideal gas initially at the same temperature. The gas pressure in Q and R are P and 3P respectively. The containers are connected through a wall of negligible volume that's initially closed. The wall is open in such a way that the temperature of the gases does not change. What is the change of pressure in Q? So here they're testing about ideal gas equation. So we know ideal gas equation says N multiplied by R constant multiplied by temperature is equal to pressure multiplied by volume. So from here we know that the NQ is gonna be equal to the pressure at Q, which is equal to P multiply volume at the Q, so 3V divided by RT. So this is equal to 3PV divided by RT. And for N sub R is same thing. So pressure at R is equal to 3P and volume at R is equal to V divided by RT is here. And after this part is open, we will say that the N sub nu, so number of moles, is gonna be equal to NQ plus, actually let me not do this, is equal to new pressure multiplied by their volume. So after this part is open, the total pressure is gonna be equal to 3V plus V, which is equal to 4V. So 4V divided by RT. And we know that N stands for number of moles, which is gonna be equal to N1 plus N2, right? So this is gonna be equal to here, this two part plus each other. And we know they are identical, so it's gonna be equal to 2 multiplied by 3 PV over RT, which is equal to 6 PV multiplied by RT. And this is equal to this equation here. So it's equal to 4 P nu V divided by RT. And now we can cancel out terms. So RT and RT are cancelled out. V and V are cancelled out. So 6P is equal to 4 new pressure. So P sub nu. So P sub nu is gonna be equal to 3P divided by 2, right? So this is the new pressure or the final pressure at this point. And change in pressure, so let me write this here. Change in pressure is equal to final pressure minus initial pressure, which is equal to 3P over 2 minus initial pressure, which is P, is gonna be equal to P over 2, right? So the answer is B. So this question is actually hard. Two containers X and Y are each filled by an ideal gas at the same temperature. The volume of Y is half the volume of X. So I'm just gonna start to label all of those questions. So let me move here. Oops. So let me start to label those questions. So the initial pressure, the volume of Y is half the volume of X. So I'm just gonna say the volume of Y is V and the volume of X is 2V. The number of moles of gas in Y is 3 times the number of moles of the gas in X. So in X is gonna be N, and in Y is gonna be equal to 3N. The pressure of the gas in X is P sub X, and the pressure of the gas in Y is P sub Y. What is the ratio of Px over Py? So this problem still is testing about ideal gas equation. So nRT is equal to PV, pressure multiplied by volume. So Px, P sub x, is gonna be equal to number of mole at x multiplied by RT constant divided by volume at x, right? And this is gonna be equal to what? So we know the mole at x is equal to N, and R is a constant, and they're at the same temperature, which is equal to T, divided by volume at x, so is equal to 2V, right? So this is the pressure at x, and Py is gonna be equal to number of moles at y multiplied by R constant multiplied by temperature divided by volume at y, and this is equal to 3N multiplied by R multiplied by T divided by V, right? So now we know that Px over Py is gonna be equal to nRT divided by 2V multiply the reciprocal of this equation here, which is equal to V over 3 nRT, and we can cancel all terms here, and this is gonna be equal to 1 over 6. Right. So the answer is A. What are the conditions of the temperature and pressure at which the behavior of real gas approximates to the behavior of ideal gas? So when you want to approximate real gas into ideal gas, there are two possibilities. The first one is low pressure and high temperature. And this is because you want molecule to be as far from each other as possible, since for ideal gas, the intermolecular forces are negligible. So this is the first possibility here, right? And the other possibility is density, is about density. So when they have low density, they can also be approximate as ideal gas. So the answer for this problem is B. Which of the following is numerically equal to specific heat capacity of the substance of a solid body? So this one is testing about the basic definition of specific heat capacity, right? So we can just directly choose B, right? So the first one is wrong. This one is not increase the temperature of the body, but increase the unit mass. Right? And you can see this from the unit of specific heat capacity. So it's something over gram, right? So this means unit mass. The graph shows the variation of absolute volume, absolute temperature T of the pressure P of a fixed mass of a ideal gas. Which of the following is correct concerning the volume or density of the gas? So when you see a graph, think about two things. The first one is area, and the second one is gradient or slope. And for this problem, we are going to think about gradient since it's about thermal physics. So when you see pressure, temperature, think about ideal gas. So nRT is equal to PV. So P over temperature over T is going to be equal to nR divided by volume here. And here, since it's a linear equation, it means that the gradient is constant. So this part is constant. And since it is a fixed mass, we know that number of moles is going to be constant, and R is also a constant. So V must be constant. And we know that the density is just equal to mass divided by volume if here is a constant. and volume is also a constant, then density will also be constant. So A is the correct answer. A ideal gas has a volume of 15 milliliter, a temperature of 20 degrees Celsius, and a pressure of 100 kilopascal. The volume of the gas is reduced to 5 milliliter, and the temperature is raised to 40 degrees Celsius. What is the new temperature of the gas? So we know that pressure multiplied by volume divided by T temperature is going to be equal to P2 V2 divided by T2, right? So this is one of the theory you will be learning in topic 3, right? And now we can just substitute number into this problem. So 15 multiplied by the volume here is 15. Now the pressure is 100 divided by temperature. And the temperature need to be in Kelvin. So we are gonna convert that to Kelvin. And the reason why I'm not doing the unit conversion is because both sides are in milliliter. So I know the unit is gonna cancel out. So I'm not gonna do the unit conversion here for the simplicity of calculation. And the other side, the pressure is 5 multiplied by pressure, which is the question asking for, divided by their temperature. Remember to convert that to Kelvin. So we are asking what is the value of pressure here. So how can we do this? So this involves a lot of calculation. So I'm gonna use some trick here. So since here the pressure, the volume is divided by 2, we know that in order for those two quantities to be equal to each other, the pressure is gonna be multiplied by 3, right? So 100 multiplied by 3 is equal to 300. And since here, from the initial temperature, from the temperature to the left side to temperature to the right side is increased. So if here is increased, the lower part is increased, the upper part gotta be increased. So the answer is gonna be greater than 300. So we can approximate an answer. It gotta be very close to 300 since here is not multiplied by a very large factor. It's probably 0 point something. So the answer must be close to 300. So you can choose B. If you want, you can definitely calculate the answer, but since calculator is not permitted in paper 1, I do recommend you to use some trick for simplicity of calculation. The molar mass of magnesium is 24 kilogram. 12 grams of magnesium contain the same number of particles of wood. So molar mass is the molar mass of magnesium is 24 kilogram. And now we only have 12 grams, which is divided by 2, so it's a half, right? And we know molar mass is saying that something 12 grams of magnesium per mole, right? Sorry, I should put it here. So 12 grams per mole. This is the molar mass of magnesium. So they're saying they're 1 mole of particle in 24 grams of magnesium. And we know that 1 mole means the number of particle in 12 grams of carbon-12. So if here it only have 12 grams of magnesium, we know that it only have 0.5 mole, right? So if you only have 0.5 mole, we know here gotta be divided by 2 as well. So you only have 6 grams. You only have the number of particle of 6 grams of carbon-12. So A is the answer. Two objects are in thermal contact initially at different temperature. Which of the following determine the transfer of thermal energy between objects? So temperature is the only factor. So D is the answer. So thermal interaction occur. Thermal energy transfer from one object to another when physical contact between two objects at different temperature occurs, right? So two objects at different temperature physically contact each other. Thermal energy transfer from the higher temperature to the lower temperature in order to reach a thermal equilibrium. An ideal gas and a solid of the same substance are at the same temperature. The average kinetic energy of gas molecule is A sub G, and the average kinetic energy of solid molecule is A sub S. What is the comparison between E sub G and E sub G? I think here should be E sub S, right? So you need to compare their kinetic energy. And how do we do this problem? So remember that temperature. So I'm gonna write this here since this is very important. So temperature is directly proportional to kinetic energy. So if you draw a graph of temperature versus kinetic energy, you will see something like this. And here is temperature in Kelvin. And here is kinetic energy. So as temperature increases, kinetic energy increases. And since for this ideal gas in this equation, they're at the same temperature, they're gonna have the same amount of kinetic energy. So B is the answer. A fixed mass of an ideal gas has a constant volume. Two quantities R and S of the gas are shown by the graph below. Which quantity do R and S represent? So pressure, temperature. So clearly it's talking about the graph of temperature versus pressure. So let me draw a graph. So here is pressure, here's temperature. So if the temperature is in Kelvin, it's gonna be something like this. Here's Kelvin. And if the temperature is in degrees Celsius, it's gonna be something like this. And here is 233 degrees Celsius negative, if I remember correctly about the unit conversion, right? And for this problem, since here is not in the origin, we know that it must be in degrees Celsius. It must be in degrees Celsius. The vertical axis must represent degrees Celsius. So R is degrees Celsius, and here is pressure. So the answer is D. A fixed mass of an ideal gas is at temperature T. Pressure is double, volume is halved. What is the temperature of those change? So this one is a simple question, just testing about ideal gas equation. So here, temperature, what is the temperature if the pressure is double? So it's multiplied by 2. I don't want to use this color. It's so ugly. So multiply by 2 and then divided by 2, which is equal to 1. So no change will occur, right? So the answer will be B. The fraction of the internal energy that is due to molecular vibration varies in different state of matters, which give the order from the highest fraction to the lowest fraction of internal energy due to molecular vibration. So it's gonna be solid, right? Since a molecule are in fixed place, so they only vibrate to generate energy by molecular vibration. And then is liquid state, since the distance between molecules are farther than solid state, but closer in gaseous state, and the last one is gaseous. So the answer is B. Which of the following correctly identify the property of molecule of a substance that determine the substance internal energy? So this one is testing about the definition of internal energy, which is equal to the total random kinetic energy plus total potential energy. So A is the answer. Polarized light of intensity I sub 0 is incident on a polarizing filter. Light from this filter is incident on a second filter, which has an axial polarization of 30 degrees to that of the first filter. The volume of cosine x is square root of 3/2. What is the intensity of the light emerging through the second filter? So this is gonna be the first filter. So polarized light is something look like this in all direction. Right. And after polarization, it's gonna be something look like this. And initially is I0, so after it's gonna be half multiply I sub 0. So when you polarizing light in a vertical direction, is you only multiply the quantity by 1.5, and then it has a volume of 30 degrees. So you are gonna multiply 1/2 I sub 0 multiplied by cosine 30 degrees squared. And this is equal to 1/2 multiplied by I0 multiplied by 3/4. And this is gonna be equal to 3/8 multiplied by I sub 0. So the answer is D. An atomic gas such as helium will approximate that a ideal gas when it kept at void. So we know a gas can be approximated into an ideal gas either when it has a low density or when it has a high temperature and a low pressure. So the answer for this problem will be B, low temperature. And this is because you want the molecule to be as far from each other as possible, since intermolecular forces for ideal gas can be ignored. Water at a temperature of 0 degrees Celsius is kept in a thermally insulated container. A lump of ice is also 0 degrees Celsius, which is placed in the water and completely submerged. Which of the following is true in respect for both net amount of ice that will melt and the change in temperature of the water? So this problem is testing about thermal interaction or transfer of thermal energy. So since it has the same temperature, we know that no energy transfer, no thermal energy will transfer. No thermal energy will transfer. So they're gonna be 0 degrees Celsius for both of the ice and the water. So no change in temperature, and since there's no change in temperature, no ice will melt. So the answer will be C. A ice cube and an iceberg are both at a temperature of 0 degrees Celsius. Which of the following is a correct comparison of the average kinetic energy and the total kinetic energy? So think about in this way. Total kinetic energy, EK total, is equal to your average kinetic energy multiplied by number of particle, right? So this is number of particle. So since they are at the same temperature, their average kinetic energy is gonna be the same, but their total kinetic energy is going to be different since they might have different number of particle. And by intuition, we know that a iceberg is definitely larger than an ice cube. So the total kinetic energy of iceberg will probably be larger than the total kinetic energy of ice cube since it maintains more particle. So the total kinetic energy will be larger since it has a larger number of particle. So the answer for this problem will be B. The behavior of real gas is different from that predicted for real gas. For ideal gas, which of the following about real gas is not correct? So gas molecule has potential energy. Forces between gas molecules are always negligible. Gas molecule has volume. Real gas can liquefy. So B is the correct answer for this problem. So we make the assumption that the intermolecular forces can be ignored for ideal gas, which is not always true for real gas since there are always intermolecular forces between a molecule. So B is the correct answer. A container of 0.6 kilogram of a liquid substance is placed on a heater. T is equal to 0. The specific latent heat of vaporization of the substance is 20 kilojoule per kilogram. The graph shows the variation of the temperature T of the substance with time T. What is the power of the heater? So we know to calculate heat by specific latent heat is going to Q is equal to mass multiply their specific latent heat capacity, which is equal to 20 kilojoule per kilogram. And since here is kilojoule, we need to convert the unit to joule, right? Since the answer are all in watts, so don't be tricked by the unit. So it's equal to 200 multiplied 1,000 joule per kilogram. Right. And if we want to calculate power, so power is equal to energy, which is equal to heat energy in this case, divided by time. Right. And this is what we want for this problem. So we know the mass is equal to 0.6, and we know their latent heat capacity is equal to 100 multiplied by 1,000 divided by change in time, which is here. So 50 minus 10 is equal to 40, and this is gonna give us the answer of 3,000. So the answer will be B.